This lesson is on predicting products. It's part 3. We'll be looking at combustion reactions, decomposition reactions, and some synthesis reactions. So we're going to start out with combustion. Now, the synonym of combustion is burning. So anytime something is burning, it is undergoing a combustion reaction. And for combustion, you must have oxygen as a reactant. So that is how you can know that you have a combustion reaction. If you have O2 and you get heat and energy, then you have combustion. So we could have, for example, some phosphorus, and sometimes you'll see phosphorus written as P4, sometimes just P, sometimes P4. And if we ignite that in oxygen gas, then we will get P4O10, tetraphosphorus decaoxide or decoxide. And to balance that, for phosphorus, we have 10 oxygen, we need 10, so I'll squeeze a little 5 right in there. So this is a combustion reaction. This is also a synthesis reaction. When you have 2 reactants that yield a single product, that is also synthesis. So this reaction falls into 2 categories. For combustion, there's a very important class of combustion reactions, and that is combustion of hydrocarbons. Hydrocarbons. So when you have a combustion reaction, you have oxygen as a reactant. The other reactant is your fuel. So here we are going to be talking about our hydrocarbons as fuel. A hydrocarbon is a compound containing, surprise, hydrogen and oxygen. So when we write the formula, the carbon goes first. So CX for the number of carbons, HY for the number of hydrogens. Now, when we have what is called complete combustion, which is good, clean burning of hydrocarbons, we get, for our products, water and carbon dioxide, no matter what that hydrocarbon is. Again, complete combustion. If you have incomplete combustion, then you can get some other products, but we're just going to be concentrating on when we have complete combustion of a hydrocarbon. So the simplest example of that is when we light our Bunsen burner on fire. Our Bunsen burner, the fuel is methane gas, which has the formula CH4. When we light our Bunsen burner, the methane gas combines with the oxygen in the atmosphere. And when we adjust our Bunsen burner to get that good blue flame, we have complete combustion. Then our products are, I usually put the carbon dioxide first, CO2 and H2O. So from the heat that is given off, that H2O is going to be in the vapor phase, and the carbon dioxide also in the gas phase. And then we need to balance. I call these CHO reactions. So balance carbon first, then hydrogen. Always leave the oxygen to last for these. So 1 carbon, 1 carbon. We have 4 hydrogens. We need 4 hydrogens. Put in a coefficient of 2. That gives us 2 oxygens plus 2, a total of 4 on the product side. To get a total of 4, we put in our coefficient of 2, and we're balanced. All right, let's look at another one of these. We have C3H8 gas. So this one is methane, this is propane, and we spark that in an oxygen environment, and we have complete combustion. We're going to get CO2 plus H2O. So always remember these 2 products for combustion of hydrocarbons. balance, 3 carbons, we need 3 carbons, 8 hydrogens, we need 8 hydrogens. Then on this side, count the oxygens, we have 4 plus 6, which is 10. So we need a 5 here to give 10. We'll do one more, we could have something like this, C25, H52, and that would be in the solid form. And for combustion, we need oxygen, of course. And complete combustion, we're going to get CO2 and H2O. So we have some pretty big numbers here, but that doesn't matter. We're going to use the exact same way to do it. So we need 25 carbons on this side, so put in the coefficient of 25. Then we need 52 hydrogens. So here, let's see, to get 52, divide 52 in half, we need 26. And then we're going to add it up. So we have 26 oxygens plus 50. We need 76 oxygens. So that means we need 38, because 38 times 2 is going to give us 76. So pretty big coefficients for the oxygen, carbon dioxide, and the water, but it's the exact same process. Okay, so now we're going to move on. And we'll look at some decomposition reactions. So in decomposition, we have a compound that breaks down into simpler compounds. So one of the simplest decomposition is when we have a binary compound. And this binary means that we have 2 elements. We can have any number of atoms of each element, but we can only have 2 elements. So binary compounds can undergo decomposition and break down into their elements. So for example, if we have some sodium chloride, and if we want to break this down, it's not going to happen just on its own. You have some table salt, you're never going to see that break down into sodium and chlorine. We have to heat it up and melt it, put it in the molten state, turn it into a liquid, and in addition to heating it up, we need to put in some electricity. It's called electrolysis. So we need to do some work to get this to happen. But if we do that, then we can break it into its elements, solid sodium and chlorine. And remember, chlorine is a Hofbrinkel, so when it is by itself in its elemental state, then we need that subscript of 2. And then of course we need to balance it, so we need 2 chlorines, so that means we need 2 sodiums. So pretty easy when you have a binary compound decomposition. And then we have different classes of decomposition. For example, if we have what we can call a metallic chlorate, and we want to decompose that, and again, we need to heat it up and add a catalyst for this to happen. Remember, catalyst is a substance that can help a reaction go faster. So if we have a catalyst and we heat it up, then we can get our decomposition products, which are a metallic chloride plus oxygen gas, O2. Oxygen is a Hofbrinkel. So it is an example of a metallic chlorate would be potassium chlorate. So okay, potassium is +1. Chlorate is ClO3 that has a -1. So +1, -1, they cancel out. Metallic chloride, so our metal is potassium, and potassium chloride is KCl. Potassium +1, chloride -1. And then our other product is oxygen gas. So we need to balance this. So we have 3 oxygens and 2. When you have the 3, 2, reverse it. So we put 3 here to get a total of 6. Now we put a coefficient of 2 to get a total of 6 oxygens, which means we need 2 potassium chlorides. So this could be lithium chlorate or magnesium chlorate or calcium chlorate. And then we will get lithium chloride or calcium chloride. Metallic chlorate, it just breaks off and we get the metal chloride and oxygen gas. All right, our next category is metallic hydroxides. And these will undergo decomposition again. Usually you have to heat them up to get the reaction to happen. And now this time we're going to get a metallic, metallic oxide or metal oxide plus water. All right, so for our example, we'll look at calcium hydroxide, calcium being our metal. So Ca parentheses OH2. All right, so we heat that up to break it down. And our metal oxide is calcium oxide. Calcium is 2 plus, oxygen is 2 minus, so our formula is CaO. And then our other product is water, H2O. And it is balanced just like this, 1 calcium, 1 calcium. We have 2 oxygens, 1 here and 1 here. And we have 2 hydrogens, 2 hydrogens. And then our next category is metallic carbonates. And these also break down into metal oxides. And, well, let's see what it breaks down into. We'll look at our example, and then we'll see what it breaks down into. So our example for our metal, we'll just pick magnesium. It could be calcium or strontium, whatever. So magnesium carbonate. Magnesium is 2 plus, carbonate is 2 minus, so 1 and 1 for our subscripts. And so this breaks down, when we heat it up, decompose it, the metal oxide will be magnesium oxide, magnesium 2 plus, oxide 2 minus, or formula is MgO. And then when we take the MgO out, what is left? A C and 2 O's. So carbon dioxide is our other product. Oops. Carbon dioxide. All right, so if you had barium carbonate, it would break down into barium oxide and carbon dioxide. So to predict the decomposition products, you have to remember these categories of decomposition. Okay, and we're also going to look at what if we have hydrogen carbonate. So hydrogen, it's to the left of the staircase, but hydrogen is a non-metal. Oops, I forgot. I can't even spell. Oh my goodness. Let me erase that. Okay. Wow. Okay. Hydrogen carbonate. All right, so we have a non-metal carbonate, but we're going to get our non-metal oxide, which is hydrogen oxide. Well, that's just water. And what's left, because hydrogen carbonate is H2CO3. So we get water, H2O. And what's left when we take out the H2 and O is CO2. So any carbonate, we're going to get carbon dioxide. If it's a metal, we get the metal oxide. If it's hydrogen, we just get plain old water. So now we're going to look at kind of a famous reaction. Okay, we'll call this the volcano reaction. So this, we're not talking about real volcanoes and lava. This is a reaction that a lot of students do in grade school or middle school for science fairs. They'll make a paper mache volcano and then put in baking soda and vinegar, and it all bubbles up and looks like a volcano. So we're going to actually do that reaction. So for this reaction, you take baking soda, and you probably have some in your kitchen right now. So take some baking soda, and you're going to add some vinegar to it. Doesn't matter what kind, white vinegar, any kind of vinegar is going to work. Apple cider vinegar will work. And this will react right away, and you'll get all this fizzing and, you know, fun stuff happening. So what is the reaction that happens? Well, baking soda is the chemical sodium bicarbonate. Okay, so when you do the reaction, that's solid. And then vinegar is 5% acetic acid. So that is aqueous acetic acid. 95% is water, 5% is acetic acid. Okay, so we can write the formulas for these. Sodium is Na plus the bicarbonate ion is HCO3 with a -1 charge. So we cross them and we get NaHCO3, solid, plus acetic acid. So this is an ic acid. So that means that we have the acetate ion. So the acetate ion is C2H3O2 with a -1 charge. So we're going to need 1 hydrogen to balance that for our acid. So we get HC2H3O2. And that's aqueous because it's dissolved in water. So this, I hope you can recognize that this is just a double replacement reaction. So let's put parentheses around these so we can kind of keep this straight. So double replacement reaction. The sodium combines with the carbonate. So we get sodium carbonate, sodium +1, carbonate -1. So it's just NaC2H3O2. All sodium compounds are soluble, and we have water because the acetic acid, the vinegar is in water. So this just dissolves in the water that is there. And then our other product, the H, hooks up with the HCO3. So I'm going to do that up here so we can see what happens there. So our H is an H+, and then we have HCO3 minus. So when we cross those, it's 1 and 1. We get HCO3, which we can write as H2CO3, hydrogen carbonate. So we get H2CO3. Now, we just learned that H2CO3 breaks down in a decomposition reaction, and that happens at room temperature. So as soon as this is formed, it's going to break down into H2O, liquid, and CO2, gas. So this, the carbon dioxide gas that's produced, is what causes all the fizzing when you mix baking soda and vinegar. So we have a decomposition reaction. Nope, I'm sorry. We have a double replacement reaction that is followed immediately by a decomposition reaction. Okay, so now I'm just going to give you some reactants, and then I would like you to pause the video and go ahead and fill in the products according to the type of reaction that it is. So we're going to start out with some sodium carbonate. So there's sodium bicarbonate and sodium carbonate. So they are different. All right, so we only have one reactant there. predict the products for that, and then balance it. All right, our next one. Okay. Oops. Okay. All right, so go ahead, pause the video, and then come back. Okay, so hopefully you're back. And so the first one, we only have one reactant, but we got an arrow, so that's got to be a decomposition reaction. So this is a metallic carbonate. So that breaks down into the metallic oxide, so sodium oxide. So sodium is a +1, oxygen is a 2-, so our formula is Na2O, and then our other product is CO2. Metallic oxide and carbon dioxide. And then we're all balanced with coefficients of 1s. Here we have calcium chlorate. So our metal chlorates break down into metal chlorides. So that would be calcium oxide, calcium 2+, oxygen 2-, so it's just CaO. And then our other product, oops, wait a minute, that is completely wrong. That is not correct. Let's see, let's erase that. We'll leave that. That's completely wrong. Our chlorates break down into metal chlorides, for goodness sake. So this is CaCl2 plus oxygen O2. So now we need to balance that. We'll need a 3 there, and now it's balanced. Yeah, it's the carbonates that break down into the oxides. The chlorates do not break down into oxides, just oxygen. All right, our next one, C4H8. So here we have a hydrocarbon. And unless told otherwise, we're going to assume complete combustion. So that means our products are CO2 plus H2O. All right, so to balance, 4 carbons on this side, we need 4 on this side. We have 8 hydrogens. To get 8 on this side, we put in a 4. 4 times 2 is 8. Then add up the oxygen. So we have 4 plus 8 is 12. So we need a 6 here to get our 12 oxygens. And then here we have a decomposition. So this is a metallic hydroxide that does break down into a metallic oxide. I'm not going to make a mistake this time. So we get SRO plus 2 minus 2, so 1 of each, plus our other product is water, H2O. Here it doesn't make sense to do the HOH trick because we don't have hydrogen separated from OH. So just like that. And that's it. And then for synthesis, we only did 1 at the beginning, but any decomposition, you turn it around and you'll get a synthesis. All right, so that's it.